All right, let's get started. All right, we're on the home stretch now. PS11. Remember, this week you need to meet with a TA, you and your partner if you have one. 40 points for demonstrating that you've done 4 of the things that are in the rubric for PS11. And then the whole thing will be due a week from Thursday. On Friday if you have a late day. I'll say if one of you has a late day. And there are also, both of the things I just mentioned are group activities. You need to do it with your partner. And individual activities at the end of this week and the end of next week, you need to fill out a little quiz, basically saying how things went. So don't forget to do that for a few points. I know a lot of you have been scheduling appointments. If you haven't, be sure you do that. And any questions or problems about PS11 or anything else? Yeah?
Can we go over the, not necessarily exactly how to go the bullet in the right direction from the nose of the...
Okay. So he's wondering how to point the bullet in the right direction. So when you create bullet's going to be a participant, and while I'm thinking about it, when you draw the bullet, when you make the shape for the bullet, it can't be a point. It has to have some area to it. So either a small circle, a small square, or something. If it's just a point, then it won't be detected when it intersects with anything. Nothing will blow up. So you want to point it in the right direction. Well, when any participant, you can set the position and the velocity and the direction. So where should you set the position of a bullet when you create it? Talking about ship bullets here, I guess. Yeah?
The ship distance direction.
Well, okay, so we should set the direction to be the same as that of a ship. And you can get the direction. There's a method that'll tell you the direction the ship is going in.
Okay. Rotation. The bullet should be the same rotation as the ship.
Okay, so Stefan is saying it should be the same rotation. So, yeah, I don't think I used the word. You can set the rotation of things, not the direction. So you want the rotation of the ship, and use that to set the rotation of the bullet. What about the
direction of the bullet? The direction of the bullet is the rotation of the ship.
Okay. The direction of the bullet is the rotation of the ship. Okay. Yes. Say a little louder. And right, and the initial location should be the nose of the ship. Any other questions? Yeah.
So you mentioned in the 11B that you should schedule an appointment on the calendar. Could you show briefly where the schedule button is on the calendar?
Okay, so the question is how to physically make an appointment. Let's see if I can do it. I'll have to go to student mode. Okay, so you can, somebody here can tell me how to do it. So I go here and I'll look at the current week. Okay, what do I do? How do you make an appointment? I've seen hundreds of you do it, so. Yeah. Click what?
On the right side, find appointment.
Find appointment. Select course. Submit. Okay, so there are a bunch of appointments in here that are hard to read. I guess you click on the plus sign and click reserve. Okay. Any other questions? Yeah.
If we don't have a laptop, how should we get our projects there?
Okay, he said if you don't have a laptop, how do you demo your work to the TA? You'll need to get it working on the K-Lab computer. So the room's full of computers, and you all can have free accounts on them. And put it on a thumb drive or something, or demo it that way. Be sure to get there early to get set up. Other questions? Yeah?
What's the best way to get input from the key event and so it can work with the refresh time?
Well, okay, so this is sort of a hint. I like giving hints. If you want things to happen smoothly, like if you want bullets to fire smoothly, you say you hold down the key and the bullets start firing. If you fire a bullet every time the key press event shows up, what's going to happen? Yeah.
It's going to be like if you type a letter, it's going to go once, stop, and then
Right. You'll push down it, as soon as you hit the key, it'll fire a bullet, and then there's a delay before it starts auto-repeating. So you get boop, and then boop, boop, boop. That's not smooth. Same thing will happen if you turn. So if you want something to happen smoothly, it needs to happen on the refreshes every 30th of a second. Okay? So you need to notice when the key is pressed. The way to think about it is, don't fire things when the key is pressed. Fire things and turn things while the key is pressed. So you need to know when the key is pressed and also when it's released. If you can keep track of whether the key is down at a given moment in time, then somewhere else you know when to do things. So it just takes some extra instance variables to keep track of whether firing is in progress or turning is in progress. Now, I recall we always have this problem with the arrow keys. So there are keyboard limitations with the arrow keys where I don't really think you can work all the arrow keys at once. So if you're really a hardcore video game player, I play with one finger, so it's not a problem. So you need to use the ASDF. The hardware for ASDF is better supported than the arrow keys. Any other questions? Okay, well, if you think of any later, let me know. Okay, so we've spent the first 13 weeks of the semester talking about programming in Java. And you can go through that and start to think that computer science is all about programming, and it's not. If you go on and take more courses, you'll see that. So what I'm going to spend the next 3 lectures doing is talking about some topics that aren't directly related, that aren't pure programming. We'll look at some things having to do with engineering and some things having to do with more scientific side of computer science. And today what I want to talk about is how Java works behind the scenes. And I'm going to talk about 2 things. One is, I'm going to talk about what happens when a Java program is compiled. Show you how that works. And then I'm going to visit a topic we briefly touched on earlier in the semester, which is the stack and heap model. Because the longer you put off understanding this runtime memory management model with the stack and the heap, the more regretful you'll be when you finally do figure it out, because it makes a lot of things easier when you understand the model. So we're going to play around with this program today. This is the myArrayList that we did early in the semester. So remember, it has an array of elements and an integer that tells you how many elements are actually in the list. And every time the list when the array fills up, we double its size. So we don't have to double it. We don't have to keep increasing every time we do an insertion. So these are the methods. In particular, look at the main method right there. So what the main method does is it creates a new array list, my array list, and then it inserts the numbers 0 through 4 into the list with add last. Then when the loop ends, it goes and gets element 3 out. And finally, it removes the last element in the list. So that's what it looks like in Java. What we're going to look at now is what it looks like in a different language. This is the rest of the class, which isn't important right now. So when you in Eclipse, when you write a source file, a Java file, and you save it, it's automatically built, automatically compiled. It's automatically translated into bytecode. And if you've poked around, you don't see the class files in Eclipse. But if you go into a file browser and just browse into your workspace and browse into a project and go into the bin folder, you'll find class files in there. So every Java file gets turned into at least one class file. So .class is what it's called. And if you look at a bytecode file, at a class file in a text editor, it'll just be gibberish because it's a binary file. But there's a program that ships with Java that you can use to look at the contents of a class file in a human readable form, which is what I've done. So it's called Java P. And so I ran Java P on that myArrayList class. And this is part of the bytecode for the main method. So this is another programming language. This is what your program is translated into before it's run. So the Java virtual machine executes bytecodes. The Java virtual machine doesn't see your Java source, it sees this. So you can think of these as instructions to the Java virtual machine. Now, I'm not interested in you becoming experts at Java bytecode. I just want to give you an idea of what it looks like and how it works. And it's not necessarily the case you'll ever look at Java bytecode again, but you'll definitely look at similar things, assembly language. So Java bytecode is a kind of assembly language. Assembly language being a low-level language that's to which high-level programs are translated. So you take a class like 3810, you'll get in detail into an assembly language and you'll write assembly language code. But here I just want to get your feet wet. So I've added these comments over here. So really this is the bytecode. And this number here is, you can think of it as a line number, but it's really the byte number. So this first instruction, new number 1, actually takes up 3 bytes. Byte 0, 1, and 2. And then, how many bytes does that instruction take? The one that starts at byte 3. Yeah, it takes 1 byte because the next instruction comes at byte 4. So bytecode instructions can take 1 or more bytes to represent. And so these line numbers become important, but not at the moment. So let's just talk about what happens. So main has been called. The main method has been called. And the first thing that has to happen is a place on the stack must be created where the local variables can be stored. And so the Java virtual machine would do something like that. So there is, remember the main method had a variable list which contains a reference to a myArrayList object, and it contains an index I that it uses in the loop. Okay? So the Java virtual machine creates, the stack is just a place in memory where the values of variables are stored and where other things are stored. And in the stack, let's just not. It's not going to work to use the mouse there. At the top of the stack right now, we have a place to store lists and a place to store I. And that's what the Java virtual machine uses to store things. So once it's got the stack set up, it begins executing. And it says new number 1. And what new does is it creates a new object and pushes the reference to the object on top of the stack. And how does it know what kind of object to create? There are lots of objects out there. Yeah? Okay, he said, does it create a myArrayList because we're in the myArrayList class? No, we could be creating any kind of object from main. So looking at the code, yeah?
Does it create a general object because it just extends every other?
He asked, does it create a general object, like a base object with a capital O? No, it creates, this instruction here creates a myArrayList object. Yeah.
It creates a myArrayList object because a myArrayList is what number 1 is referring to.
Right, so that number 1 is, you can think of that as an index into a table, and the table contains a string that says what type of object, or I don't know if it's a string necessarily, but information about what object to create. So that's where the other 2 bytes go. Right, so byte 0 has the code new, and the next 2 bytes have that number 1, basically. This is human readable form, but the next 2 bytes are information about which type of object to create. So what the virtual machine does is it goes off and creates an object, and what does it do with the reference? How will the picture look different when I go to the next frame of the animation here? What's the comment say? Anybody want to take a chance? Okay.
It'll put the reference to the object on top of the stack.
Right. So push means push it to the top of the stack. So the big box there on the slide is, think of that as all the room there is on the stack, but the only parts that are used are at the bottom there, list and I. And so when I say push a reference, so it creates the object, and all right, so let me explain what I'm doing here. When something is highlighted in green, that means it's about to be executed. So there it is. It gets executed, and a reference to a myArrayList object is pushed on the stack. So now there are 3 things on the stack. A place to store a list, a place to store I, and at the top of the stack is myArrayList object. So we see that the stack contains places to store the local variables, but it also has temporary, the space above that is used to store temporary values. Okay, so it got created. Next thing that happens is we execute this simple bytecode that says duplicate. It says whatever's on top of the stack, duplicate it and push it. So what will the picture look like now? It's just going to take whatever bits are on top of the stack and push it. Yeah. Right. It pushes and it copies that reference. So it's the same reference to the same object. Now, why in the world do you think it did that? Why does it duplicate the why 2 references? Wouldn't 1 reference be good enough? And you notice neither of them is where we want the reference to be. Where do we want the reference to ultimately be stored? In the variable list. So right now there are 2 references on top of the stack. So this is what it's like when you look at the code that's output by a compiler. It's just what the compiler did. It has a reason. You can't see it yet, but we'll see it shortly. Okay, so far we've allocated an object on the heap, stored the reference on top of the stack, and then duplicated the reference. The next instruction that's highlighted in green there says invoke special. That's an instruction that's used to run a constructor, among other things. And number 12 is referring to the myArrayList constructor. Again, think of that as an index into a table somewhere. So we're asked, what the Java virtual machine does is says, okay, it's time to call the constructor. Right? So let me show you what happens. First of all, what parameters have to be passed to the constructor? I'll go back. Okay, there's main. There's main, and there it calls, first line it calls myArrayList constructor. So what parameters have to be passed to it? Yeah? Well, he said this, and that's close, but there is no this in main. Yeah, so what has to be passed is the object to be initialized. So think of the constructor's initializer. And so, okay, to call the constructor, we need to give it a reference to the object that needs to be initialized. And, conveniently, what's on top of the stack? A reference to the object needs to be initialized. So what you'll find is that when the code is setting up to call a method, it pushes all the parameters on top of the stack. So I'm going to go to an intermediate state here, and I'm going to show you the only thing that changed is I labeled I put it, first of all, I put it in a solid line. I labeled the box that was at the box that was previously at the top of the stack. I have to be able to push it to the point here. So, okay, so this thing here, which was originally on top of the stack, when I go forward, I put the label this in it. These labels aren't around at runtime. They're there to make it easier for you to read. Okay? But this is the name of the parameter from the point of view of the constructor. And then I also pushed, right above that parameter, line 7 of main. And what that is the next statement that ought to be executed when this constructor is done. Right? The next piece of bytecode that's supposed to be executed. Now I want to warn you, don't take what I'm showing you here as the gospel truth of exactly how a Java virtual machine works. I'm doing sort of a plausible job of showing how it works. There may be details that aren't quite right, but the basic ideas are right. So essentially, taking that solid blue line, the thick blue line as a cue, what have I done here? What am I in the process of doing? I'm getting ready to call a method. What does the method have to have before it can run? What did the main method have to have before it could run? Yeah? Well, we have to pass it a reference, yes, but what's the very first thing we did to the stack when the main method was called? Or before the main method was called, really? Yeah?
Do you have to initialize the virtual machine?
Well, yeah, we had to initialize a virtual machine, but that's in the past. That just happens once. Yeah?
You have to initialize the variables.
Well, we have to initialize the variable this that we're passing as a parameter. Okay? Bottom line is, every method needs a stack frame. So the idea is, these three things down here is the stack frame, the current stack frame for main. And what we're building up here is a stack frame for the constructor to use. And so notice what the constructor is going to find. At the bottom of its stack frame, it's going to find its parameters. There's only one. And the next, right above the parameters, it's going to find this address in memory. And then it'll use the rest of the, more of this memory up here to do whatever it needs to do. So we created a stack frame containing the parameters and the return address for the constructor to use. And now the constructor will run. And when the constructor finishes, what it's going to do is, so we're going to go to the first bytecode instruction for the constructor and start running. When it returns, which instruction will run next? What's the Java virtual machine going to do when the constructor says return? Return to whoever called me. Yeah.
After the constructor returns, what has been returned will be assigned the reference on the left-hand side of the array.
Well, you're sort of getting ahead of the story. The constructor is going to contain a bytecode that says return. What's the next byte of code? What's the next piece of bytecode to be executed when the constructor does that? Yeah?
Top of the stack there, line 7 of main, so it'll go back to that line.
Exactly. What's going to happen is it's going to look at its stack frame right here and say, okay, the Java virtual machine will, and it'll say, okay, since I'm done with this stack frame, I should go back and start executing line 7 of main. And so I'm not going to animate the call of the constructor. So the constructor is going to go out to this myArrayList object and fill it in. And then the stack will be popped. The entire stack frame will be popped. and control transfer to line 7, because that's what it says in the stack there to do. So you can see that happened right there. So we were there. The stack frame for the constructor is sitting there on top of the stack, and when the constructor returns, its stack frame is wiped out, and control resumes at line 7, because that's what we said to do right here when we called the thing in the first place. So it's expecting to find the line to pick up with right there above the parameters. So now the constructor is run, the array list is initialized. Okay? Now, what happened if we back up a little bit? Remember that we duplicated the reference on top of the stack. So what happened to the one at the top one? Right now there's 2 references on the stack. Initially, let's go back here. There were 2 references on top of the stack. One of them was there so we could pass it to the constructor. But what happens to that reference? Yeah? Yeah, it's consumed. When the stack frame is popped, it goes away. We're in this state. So it's a good thing we did that duplication, so there's still a reference on top of the stack. Now the next thing we want to do with that reference is store it into the variable list, because that's what the code said to do. List equals new myArrayList. And so that's what a store 0 does. A store 0 stores the top of the stack in variable 0. Okay? So variable 0 is the variable at the very bottom of the stack frame. So I'm saying list because that's just to help us understand what's going on. The Java virtual machine isn't looking at variable names. It just says, take what's stored here and put it down there in location 0. And so we go forward and you'll see, so it pops the thing that's on top of the stack and then shoves it into variable 0. Okay? Next thing that's going to happen is we push a 0. 0 goes on top of the stack. And then it says, I store 1. That means pop what's on top of the stack and store it in a variable 1. So what's going to change here? The 0 is going next to I. The 0 will be popped and it'll be stored next to I. Now, you may be wondering, why do I say A store 0 in one place and I store 1 in another? Why A and I? Anyone want to take a guess? Why are these different store operations? Why isn't it just store underscore 0 or store underscore 1? Yeah.
Well, one is a reference variable and the other is an integer.
Yeah, one's a reference and one is an integer. And so there's just a different instruction for storing an integer or storing a double than storing a reference. Okay? All right, so we have, what we've done so far is we've initialized list. Remember that the main method said list gets new array list. So we've done that. And then a for loop begins, and the first thing the for loop does is assign 0 to I, and we've done that. And the next thing it says to do is go to line 21, go to byte 21. And you'd be wondering, why do we do that instead of just putting what we want to do next here? But we'll do what it says. That just says, instead of executing, go to a different place. So I'm going to hit it, and this is more of the bytecode for the main method. And suddenly we're executing at byte 21. Now, what has to happen right about now? Remember, we've got a for loop that's letting I run from 0 up to 5. And each time through the loop, we're going to call a method. So I is going to count 0, 1, 2, 3, 4, before it finally hits 5 and is too big. So what's the first thing a for loop has to do? As soon as that for loop sets I to 0, what's it got to do? Yeah? You got to check. The condition is I less than 5. Right? So for I equals 0, while I is less than 5, I plus plus. So what happens is we've got to compare I to 5 and see if it's less than 5. So what happens is it says I load 1, which means push the number 1 on top of the stack. I'm sorry, push variable 1 on top of the stack. So we take whatever's stored in variable 1 and push it on top of the stack, and then it says push 5. So that isn't variable 5, that's the constant 5. There it goes. And then we have this instruction that compares two integers that are on top of the stack. And if it finds out that 0 is less than 5, it'll go to line 13. If it's not, if 0 is not less than 5, where would it go? It would just go to the next statement, which is probably line 25, probably. Okay? But we know 0 is less than 5, so what's going to happen is it's going to pop 0 and 5 off the top of the stack and then transfer it to line 13, because we know 0 is less than 5. So that's what it does. So we're back now to our stack only containing our local variables. So you notice we're using the stack to hold the values of variables, and then we're also using the top of the frame to hold temporary values that need to be used. Okay, so we've done that part, and now what has to happen is we need to call the add last method. So we're in the body of the loop now, and the instruction is list dot add last, and the parameter is I. So let's see what we do. We push var 0 onto the list, onto the stack, and we push var 1 onto the stack. Now, why do we do that, and why do we do it in that order? What's the point of getting the reference to the array list and the number 0 on top of the stack? Yeah?
So that you can do stuff with them?
So we can do stuff with them. In particular, what is it we want to do with them? Yeah?
We're going to add last, and that'll get popped off.
Okay, well, we're setting up to call add last. And what's our job? Our job to call add last is to set up its initial stack frame, right? So what we've done is, by pushing these two things on the stack, is we have created a stack frame for add last to use that contains the parameter this, which refers to an array list object, and its parameter e, which is 0, plus we push the information that when this method is finished, pick up with line 18. And now we transfer control to invoke virtual transfers control to the add last method. It'll run, it eventually hit a return, and when it sees the return, it'll say, oh, I'm supposed to return to line 18 of main. And boom, I'm back here. So the way we get back, we have to tell the method we're calling where to go back to when it's done. Great. Now, why didn't anything change, though? What did add last do? What lasting effect did add last have? Yeah?
It changed the myArrayList object.
Right. It changed the myArrayList object, but I'm just not showing you that detail. Okay. Here's an interesting instruction, INC. What that does is it adds 1 to the variable in the variable 1. So it's a special instruction to add 1 to something. There's not a special instruction to add 2 to something. To add 2, you'd have to load the contents of variable 1, push it on the stack, push a 2, and then use an add instruction, and then store back. So why do you suppose that would take 4 steps to do? If it was any number other than 1. Why does 1 get special treatment? Why does adding 1 get special treatment? Yeah?
Maybe it's already in binary, so you don't have to convert it over.
Well, he said it's already in binary. That's not the key idea, yeah.
Well, in like the Java code we write, we have no plus, whereas for any other number you would have to do plus equals.
Okay.
And so on.
All right, so he's saying there's I++. Of course, just because it says I++, we can still compile it as load, add, store. Bottom line is what? Yeah.
Because it's so common.
Because it's common. So you can't have these things, these bytecodes, these are often called opcodes, operation codes. You can only have a limited number of opcodes. So you use them for things that are common. And you make things that are not common take more instructions. So adding 1 is going to be a lot faster than adding 2. Okay, so we execute this instruction. So what will change about our picture here? Yeah, it'll add 1 to I, so I will change to 1. Then we're going to push the contents of var 1, and we're going to push 5. Setting up for the comparison again. We've got to find out if 1 is less than 5. Okay? But I don't want to go through that loop again 5 times. So I just changed I to 5 here. So let's pretend we've already spun through and I got incremented. We did a bunch of add last, and now I is 5. So what will happen next when it does the comparison, since 5 is not less than 5? Just goes down to the next instruction. So now we're there. So the stack, on the stack I has 5, list is still referring to that object. And it says to take the contents of variable 0 and push. So we push it. Then it says to push the constant 3. Now here again, yeah, there's a special instruction for pushing 3. If you want to push a larger number, it'll take multiple instructions to do. But for small integers, they put in special instructions to push them. So let's push 3. And why would we be pushing a reference and the number 3 on top of the stack? Yeah?
Set a stack frame.
Right, we're creating a stack frame because we're getting ready to call get. And we got to pass get, the object on which the method was invoked. And 3 is what we're trying to add to the list. And so here we are, sort of an intermediate state. I'm emphasizing that we've got things set up just so for get, so that it has this as variable 0, its variable 0. And it has E as its variable 1. This is what it's expecting. And then we call it, and it'll run, and when it's done, it will transfer to line 31, because we told it to transfer to line 31 when it was done. But what else does get do? What does get do that the method and the constructor didn't do? Return something. So we've seen before that when the method returns, it removes the stack frame from the stack, leaving the original stack frame, then transfers to the indicated line. So where would be a good place for that method to put the value being returned so that main can access it? Yeah. Yeah, it just puts it on top of the stack. So we're trying to get the element at index 3, and it turns out to be a 3. And so the method runs, and I'm not showing the animation of that method running, but when it's all done, it's going to pop its stack frame, it's going to leave a 3 behind, and then it's going to transfer to line 31. And that's what you see. And now the main method runs again. It assumes that the answer it wanted is sitting on top of the stack. And the first thing it does is pop it and throw it away. Why are we popping it and throwing it away? What did the original method in Java do with the value that's returned? Probably don't remember. Given that we're throwing away the thing that came back on top of the stack, what do you suppose it did? Yeah. Yeah, well, it just didn't do anything with it. It just called get and didn't store the result anywhere. So if we went back, it's a number of slides back. But the Java code just called get, but then did nothing with the return value. And so the generated code has to pop it to get rid of it. Now, if what it did was actually print it out or something, then or store it, we would have some other instruction here to store it or print it out. But since we do nothing, we just pop it, so it goes away. And now the last thing we have to do is remove the last element from the array list. And again, we push that list, the reference to the list. That's the only parameter that remove last takes. It just takes a reference to the object in which the method was invoked. So we are setting up to call remove last. We created a stack frame. We told it to return to line 36. and it does its thing and returns to line 36. And then we hit our return. So what should we do? Yeah?
Pop the stack until it's empty.
Well, we're going to pop our stat frame. And presumably when we were called, we should have gotten a location to resume, to transfer to when we're done. I didn't show that at the beginning because I didn't want to confuse things. But at this point, what we would do is we would say, okay, we're done. I'll transfer now to whatever I was told to transfer to. And who knows what happens after that. Maybe perhaps this isn't the entire stack. Maybe there's more stack down below we knew nothing about because we never look below. We just look at our frame. Yeah?
What does invoke virtual mean? What is the number 23?
Okay, invoke virtual means calling a non-static method. That's the instruction for calling a non-static method. And number 19 just means that at place 19 in the table is the information about which virtual we'll call. 23, so 19, you think of 19 as just identifies the get method, and 23 identifies the remove method. Okay? All right, so lots of details there, but let's focus on the big picture. What do you see as the difference between, suppose I ask you to write your next assignment, your asteroids program, directly in Java bytecode. I could have done that. I could take the program and run it through Java. I could compile it, run it through Java P, and just give you bytecode and say, work on the bytecode. What would the experience be like?
Very tedious.
Be very tedious, very error prone. Why is that? I mean, you're not used to the language, but you could teach yourself. You know, probably a couple hundred of these opcodes that you can teach yourself. What would make it hard? I'm not disputing it. I wouldn't volunteer to do that myself, but yeah. Okay, it's not, you know, look at it, it's just flat. It's not structured. You can't easily see where the loops are. I mean, where is the loop? How can you look at that and tell that there's a loop? In fact, this sequence of bytecode here is a loop. So loop implies repetition. So what instruction is it that makes it into a loop? Hmm?
The one that says jump back to 13.
Yeah, this one right here that says, depending on the outcome of comparison, either continue on, i.e. leave the loop, or go back to the beginning. So it executes, it goes back. It executes, it goes back. So that's the loop. But there's no visual cue. I guess we could put in visual cues if we wanted to. Okay? Any other ideas about why this would be hard? Yeah? Okay, so he's saying you got to do very specific things. You got to push the parameters on the stack in just the right order. And if you don't, things don't work. Details you didn't have to worry about in a high-level language. Right? Lots of low-level details to worry about. You got to, I mean, before you can even store a value into a variable, you've got to figure out what that is and use a different instruction. So for storing, imagine if, you know, the assignment statement, which uses an equal sign. What if there was a different symbol that you had to use if you're assigning an integer or a double or a reference or a Boolean or a character? And you had to memorize which sign to use in each case. That'd be kind of a pain. Okay? So this, yeah?
And also in Java, when you make errors, especially in exploits like either already lets you know that you're kind of where this you can show they just
Yeah. And, you know, debugging would be, you know, when you ran the debugger, you'd be stepping through these statements like I just did, these bytecodes. So this is what programming was like in the 50s. They didn't use Java bytecode, but they programmed in assembly language. And just before 1960, people started creating higher level languages, such as Fortran or COBOL or Lisp. And the programmers at the time said, this is heresy. How can a compiler create efficient assembly code? There is no, they said that, there is no way that a compiler can create code that is as efficient as what I can craft by hand. And that may have been true for small enough programs, but once there are higher level languages, suddenly it's possible to write bigger programs much more efficiently. And the same has been true of every single advance in programming languages. Someone would invent a better way to do something, a more convenient way to do something, and the existing programmers say, this is heresy. It's going to make programs inefficient. And it's true. If we had the time and patience to go and spend the enormous amount of time it would take to handcraft assembly language directly, we might be able to, outcompete a C++ compiler, but not by much. Compilers have gotten really good. Okay? So just be thankful that you got to learn Java instead of having to learn Java bytecode. All right? All right, let's take a break and we're going to look at, we'll go to a higher level but still looking at stacks. All right, let's get started again. All right, now we've looked at a really low level of how stacks work. So I want to look at it at a higher level. And I want you to think of that box right there as the memory that's available to your Java program. And I want to show you how it's organized, or a way to organize it, not necessarily the way. So first of all, you got to have some place to store your code. So part of the memory that our Java process gets is going to have a place to store the code. And the interesting thing about the code is it can be read-only. There's no need to ever write into the code. Code that changes itself as it's running is called self-modifying code. And as you might imagine, self-modifying code is really tough to deal with. It's hard enough to understand what your program does when it's just sitting there, you know, not changing. But imagine if you could change your program as it ran. So there's our code. We also need space to store the stack. And so we're going to store the stack right next to the code. And we're going to, as the stack grows, it'll grow by stack frames. So there's where the first stack frame goes. A method is called, a method is called, a method is called. So you see we're efficiently using memory. There's no wasted space. Then method returns. Stack frame is reclaimed. What's involved? How complicated is going from that state to that state? What does the runtime system have to do? What does a Java virtual machine have to do to pop a stack? What do you think? Is it expensive? Is it cheap? Yeah? Yeah, he said, don't just throw away the variables that are in that frame. Basically, it looks like that we have to sort of wipe everything out. But in fact, what we have that I haven't shown you is at any given time, the JVM knows the address at the top of the stack. The address in memory at the top of the stack. So to pop a frame, what do you have to do? It just involves this finger here. You just move it down to the top of the following stack frame. So it just involves changing one number stored somewhere. So all the stuff that was in that stack frame is still there. It's just garbage now. We're going to overwrite it later. So pushing and popping is really efficient. So stacks tend to grow and shrink and maneuver with time. So at the other end of our memory, we're going to put a heap. And the heap is where objects are created, stored. Then the stack, as you know, has references into the heap. The heap, on the other hand, does not have references back to the stack in Java. C++, all bets are off. You've got all kinds of things going on in C++. C++, you have references from the stack into the stack, which leads to trouble. So we got the heap, and things get allocated on the heap of different sizes. You know, you create a new array list, there's some space. You create a new string, there's some space. So things are different sizes. And there's a memory manager that takes care of figuring out where to put the objects. So it makes sense as you allocate objects just to put them together in a dense stack like that. So how much free memory do we have? What is the free memory that we have as our program is running if we use this model here? That white space in the middle. So if the stack ever grows into the heap, or the heap ever grows into the stack, you got problems. Either you got a stack overflow, or your heap is exhausted. Okay? Every now and then, objects that were previously on the heap are garbage collected. So why would that one go away? What would make an object go away? Yeah? Right, there are no more references to it. So maybe the stack frame that contained the only reference to that object has been popped. So what happens periodically as the program is running is the garbage collector will run for a while. So sort of stop what's happening. You know, the program stops briefly. The garbage collector runs. It runs down the stack, finds all the references, finds all the things that are still referenced, and gets rid of the ones that aren't. Okay? Now what's the problem with that? We just deallocated an object. What's the problem with that? What can you see an issue? Yeah.
It's not like pushing all the way to the back. It's just
Right. We now it doesn't. You know, it's not like popping a stack. The stack stays dense. But now we got a hole. So what can we do with that hole? Yeah.
only put something exactly that size.
Right. So the memory manager has to remember where the holes are and how big they are, and it'll try to use them the best that we can. All right. So we allocate another object, and then we deallocate that one. Now we got a bigger hole. We allocate a small object. That object wouldn't fit in the space remaining. Now we got a new one. Now there's a little one, and so on. Okay? Now what can happen as your program runs is the heap can get quite fragmented. So there's just holes all over the place. You got lots of free space, but none of it is, you know, it's not coalesced into one big free block. So in fact, what garbage collectors also do is they will sweep through and recompact the heap when necessary. And I haven't animated that, but you can imagine once you figure out what the garbage is, it could copy all these, everything over and fill into the, you know, push everything over to the right. Now, what else do you have to do when you push all the objects to the right? You can't just do that or the program will stop working. What else, what other bookkeeping would you have to do? Yeah? Right, there are references on the stack to these objects, or there are also references in the heap to other things in the heap. You have to find all those references and fix them up. So this sort of thing, for years and years, has been a hot topic of research. People are always looking for better ways to do compacting garbage collectors. And you know, I mentioned before the break that every programming language advance is met with naysayers, and garbage collected languages were definitely met with naysayers who said, you know, it's too inefficient to have the runtime system decide where to put things on the heap and dealing with compacting garbage collecting. But you spend some time programming in C++ without a garbage collector where you're responsible for maintaining the free memory, you know, deleting when it's free, and you come to appreciate it more. Okay. Now I'm going to forget about that structure. You got a picture of how they're related, but I'm going to now zoom in on the stack. Yeah.
So just in the previous example, so like the garbage collector will go through, and then it'll go through the heap, and then it'll check if something is like not being referenced, instead of an object's not being referenced, then it'll be taken out.
Yep. So basically, one way a garbage collector can work is it finds all the references in the stack, and it follows them, and it will follow it to an object. That object may have references, so it follows those. So it just follows all the references, marking objects as it goes, setting a bit. And then once it's visited all the objects, the ones that aren't marked are the ones that get garbage collected. Yeah?
So is this as the program is running, like once you execute it, or is this like...
So it's as the program is running. So one of the early objections to garbage collectors was your program would stop, and then the garbage collector would run. So there'd be these pauses. And you don't notice it unless you're a real-time system. So if you're like the control code for a nuclear missile, it's probably not okay to pause what you're doing for 5 seconds while it's not 5 seconds that it takes, but pause for any length of time. Maybe nuclear power plant would be a more peaceful example. All right, so you're keeping a nuclear power plant from going critical. And if the program shuts down for an instant while it's garbage collecting, that's not a good thing. But nowadays, garbage collectors can run on separate threads. So you can have garbage collectors running at the same time as your code. Multi-core, yeah.
How often does garbage collecting happen?
He asked, how often does garbage collection happen? It just happens as often as necessary. So if your program isn't using much memory and there's plenty of memory available, it may never occur. So it just depends how much garbage you're generating. Now, I'll tell you one other complicating thing here is, nowadays with multi-threaded programming, you can have more than one thing going on at a time, which means more than one stack. We won't get into that. But you can do multi-threaded programming in Java where you have separate stacks, separate threads of control. In other words, Think of those green highlighted pieces of Java bytecode. You have multiple of those running at the same time, each with a different stack sharing the same heap. That's beyond what we're talking about in this class, though. Okay, so here's the stack, initially empty. We're going to grow from the bottom to the top. And here's our main method. So it's the same main method we've been working with, but now I'm not going to worry about, I want to show the relationship between the stack and the heap. So I'm going to ignore the temporary things that get pushed on the stack. I'm going to ignore, explaining how you know where to return to after you make a method call. I'm just going to focus on how the variables are kept and how the heap is used. So there's our stack frame. Green means it's about to be executed. Now I'm going to run through this once without any objects. I'm just going to look at the stack. So we're about to call the constructor, so we know a stack frame gets pushed that contains this. And then it returns. And then we get into the loop and we got to call add last. So that gets pushed. Then it returns. We go around the loop again, pushed, return. Again, push, return. Fourth time, push, return. And I think the fifth time, we finally get to the point where our array is full, and we got to do the doubling. And so what happens here is we call the copy of method. I'm just speculating what its parameters are called. So now we got 3 stack frames pushed up. Then it returns. We return from add last. Then we have to call the set method, which involves push. It returns. We call remove last, and it returns, and the method returns. So at that level of detail, you just see stack frames contain parameters and locals, and every time a method is called, a stack frame is pushed. And every time a method returns, a stack frame is popped. So it grows and shrinks, grows and shrinks. That's the key thing to remember. The stack frames contain the values of the variables. Yeah?
If a program is going to loop through something and it knows it's going to be like taking multiple copies of the same stack and just copying and putting it, is there like a way for it to like remember that it's there?
Okay, so he's suggesting an optimization, which would say, okay, you look at this loop and you see it's going to be pushing a stack frame, popping it, pushing, popping. Could it just push it once and keep reusing it? Yes, that's a plausible compiler optimization. So a compiler could generate more efficient code in that special circumstance. Just depends on how hard you want the compiler to work. Now let's bring in the heap so we can see what's actually happening. So there we are. We've just pushed the stack frame. We've got to create a new array list. So the first thing we have to do is allocate the object. So it's uninitialized at this point. The list refers to that object out there, the myArrayList object, which has room to store the size and the number of elements. Okay, the next thing that happens is we call the constructor. So we have to push the stack frame to the constructor, and notice we push this, which refers to that object. And then what's going to happen is these 2 statements execute. This.else gets new int 4, for example. How will that change my picture? Yeah. Okay, I'm going to create an array out there in the heap, and I'm going to store a reference to it in the object. Okay? Then I change count to 0, and then the constructor returns. And so what you're left with is an initialized myArrayList object. Okay? And it happened because we called a method and passed it a reference to that uninitialized ArrayList object. It initialized it and returned. The stack frame was popped, but before it was popped, because the 2 stack frames are referring to the same object, one reference is preserved. So that's the stack and heap model. Some instructions modify the stack, some modify the heap. Frames are popped and pushed when methods are called and returned from. What changes a value stored in a frame? What kind of statement would change what's stored in the I box or the list box? There's only one statement. There's only one kind of statement that'll change what's stored in the stack frame once the method call has been made. You use it all the time. Yeah. The assignment statement. That's what assignment statements do. What changes what's stored in an object? Yeah?
Is it also an assignment statement?
Okay, so let me back up here. Depends what you want to call this right here. Yeah, it looks like an assignment statement. So assignments can be used to modify what's stored in an object, or method calls can be used to modify what's in an object. But when you're assigning to a instance variable, that doesn't modify the stack. Assigning an instance variable modifies the object. So it just depends on what's being assigned to. Okay. So I get to this point, I has a value of 0, and I'm about to call list.addLast of I. So what stack frame will be pushed? You should be good at this by now. We're up at a higher level. So what information will be pushed on the stack frame? Okay, what parameters does addLast take in other words? Yeah? This and I think I call it E maybe. Yeah. So the parameter to addLast is called E for element, and this is the object with which the method was invoked. So since we said, if we go back to how we called it, we said list.addLast of I. Whatever list is becomes a value of this, and whatever I was becomes a value of E. So those values are just copied up. And now that can run. And we get to this point, and we have to increment count. Well, we get to this point, we've stored a 0 into the first element of the array, and we've incremented count to 1. Now the method returns, which pops the stack. Now we're back. I has changed to 1, so we call addLast again by pushing the stack frame. And what will happen now? When we find that this .count is not the same as this.else.length. What will these two instructions here do? What will change about my picture here when I execute the rest of this method? I'm going to go out on a limb. Like, what will change when this statement here is executed? Yeah?
Whatever is that count will change to E, which is 1.
Okay, so whatever E is, so E is a 1. A 1 will be stored into this.else, which is this array. At what index will it be stored? At index this.count. This.count is 1. So it's going to change that thing to a 1. And then it's going to change this count to a 2 when it does this.count plus plus. And there you see it. So the method changed what's on the heap. Notice all of these things start with a stack. This.else. So this.else takes you to here. This.count takes you to here. So when you spell everything out and don't make this implicit, when you refer to a field in an object, an instance variable in an object, it always is rooted in the stack somewhere. You start in the stack and you follow these arrows. So dot means follow the reference. Okay? So we return. Now we're gearing up to call addLast again with 2. So again, the stack frame appears. The array changes, the size increases. The method returns. Okay, back again. Now I is 3. So we're going to store a 3 at index 3 and increment count to 4. Good. And we return. We do it again. I is 4 this time. So we call like that. But this time, this.count, which is 4, is the same as this.else.length, which is 4. So we're going to have to execute, we're going to have to call array.copyof. So that means we've got to push a stack frame that contains the parameters to arrays.copyof. And notice the one parameter A is the reference. So we're passing a direct reference to that array the object contains. And we're passing 8, which is the desired size of the array. And it's going to give us back, it's going to return a copy that's twice as long, but has 0, 1, 2, and 3 at the beginning. So arrays.copyof does its thing and creates that array. And where are we going to put it? Why did we create that array? Yeah. Right. It's going to be stored right here. The statement was something like this.else equals arrays.copyof, right? So it's going to replace, so the reference to this array is going to go away, and the reference to this array will go in its place. So you get that. And then what becomes of this leftover array here with no references to it? It will eventually be garbage collected, because it's useless now. No, there's no way to get to it from the stack, so it's garbage. Okay, so that's just saying, I animated it so it happened immediately, but it doesn't necessarily happen immediately. It happens when it needs to. Okay, so our object has changed. We return now from the add last method. You know, we've added 4 in the remaining space. So here we just have the copied array. Now we set the count to 5 and we store 4 in the array, and the method returns. And now we've populated our array list with 0, 1, 2, 3, 4. Next thing we have to do is call the set method. So how many variables do we have to put into the stack frame for set? 3. So there's this. Their list is one parameter, the object in which the method was invoked. And then 3 is the index, and 8 is the value to be put at index 3. Now, one thing I realized doing this is I have not shown you any methods that have local variables. It's always been parameters. So suppose that set had a local variable x. How would the picture change if set had a local variable? Where would x appear in the picture? Yeah? Well, it's not a new object, it's just, it would be stored, you know, the parameters would be stored here, and then x would be stored next. So when your stack frame is created, you've got to have room for all the parameters and for all the local variables. Let me ask you another thing. I've told you that this and index and value, the variable names, are not stored in the stack. So when we have a statement that stores something in index, how does a Java virtual machine find the place where index is stored? Remember, the instruction says store at variable number 1. How does it figure out where variable number 1 is? Yeah.
It gets the address, so like it stores the address of the variable.
Well, it doesn't even have to store the address of the variable. The point is that that variable index is always going to be in the same place relative to the bottom of the stack. Right? So if this is 4 bytes large, then index is going to be stored 4 bytes above the bottom of the stack. So that's how the Java virtual machine can navigate around the stack frame without having the variable names present. They're just stored at fixed offsets from a known place. Okay. So now we're doing set, so we're going to change, or I just changed it. So we're about to change the thing stored at index 3. Oh, question, yeah.
Is that just because index is the first variable declared in this, and that's why it's 3 away, or wherever this ends?
Okay, so you're about to talk about the offsets.
Yeah.
Yeah, so
is it just because it's the first variable?
right, so in this style, the first parameter comes at the bottom of the stack, the second parameter is now, so the implicit parameter is first,
right.
And then the parameter list is stored the rest, you know, in that order. So that way you know at which offset any given variable is going to be stored. So the last thing we have to do is change the array, which I did right there. So the third element is now 8, and we return. Yeah?
Would this be a reference to the object you stored on the heap?
Yeah. So let's go back. You can see right there. List is the object on which the method was invoked. And so when we call the method that's being invoked, this refers to the same thing as list, to that heap object. And that's what it operates on. And then the last thing is to call remove last. So we just pass this, only parameter. And all we have to do is decrement count. So 5 goes to 4. We return. I'm done. Now, this is the final fault. I didn't tell you the full truth of what an object looks like, and I'm still not. An object actually looks more like this. So you see here, there was the 2 instance variables in the object. What have I added? What have I added to the object? Yeah?
A reference to all of the methods that the object can invoke.
Right. It's a reference to a table that, first of all, identifies the class to which the object belongs. So this object is identified as a myArrayList object. Why is that useful? Okay, so one reason it's useful is, let's say you want to invoke a method on the object. The way it's done is you go to the object, you follow that. This is called a virtual function table. You follow the reference, and you know that the method you want to call is number 3 in the table. So you go find method number 3 and you call it. So, you know, each of these methods would have, where I say add last here, there would actually be a reference to the bytecode for the method. So that seems like a waste of space to have all this, every object has to refer to a table like that. But why is it not such a waste of space? It's only a waste of one reference. The key thing is the tables can be shared. There's only one table per class. Each object refers to it. So yeah, you have to pay this price of the extra size of each object. Another reason you want this reference is when you do typecasting. You need to know what type of object it is, and that's identified there. But again, I could show you another picture and say an object actually looks more like that. You know, you might ask, how does it deal with interfaces? And it gets more complicated. Okay? So, you know, I've gone over a lot of detail here. It's not the details I care about. It's the big picture. And the sooner this stack and heap model gets ingrained into your head, the earlier it'll start paying dividends. It makes it much easier to think about what's going on, especially when you get to a class like 3810 or 4400, where you're expected to start programming at a lower level. Okay, we'll see you next time.